content of memory more local to the processor, and as a result, the processor does not have to wait for the memory bus to transfer all that information in order to process that information. This is not a hardware class. This class does not really describe the underlying hardware of a processor. But in order to understand why we want to use a sequential way and do it in the increasing order, in other words, we start from 0 and then 1, 2, 3, 4, it is necessary for me to describe at least a part of what I'm describing. So on one hand, we have caches. Okay, each processor has a certain amount of cache. And the way cache works is it preloads certain content from main memory into the cache. But the cache can talk to the processor a whole lot faster than your main memory can talk to your processor. And that's why the more cache, the better, because your processor can keep accessing content in the cache instead of the main memory. Okay? If you want a good analogy, it is almost like you can read, let's say, 1 page per minute, but you're inside the room, you're the processor. Okay? So you can take a page and say, okay, I can read about 1 page per minute. That's your speed of reading. But where are these pages coming from? These pages are coming from the county library. Okay? Somebody has to drive to the county library, and each time can only come back with, say, 1 page at a time. Okay? So for the most part, you'll be sitting in this room waiting for the person to bring in the next page. Okay? That's basically how slow the memory bus is compared to your processor. So how do you speed up the process? You speed up the process by maintaining a cache. What a cache is a local pile of paper. Okay? So you can basically say, this room has enough capacity to store a pile of paper up to, let's say, 32 pages. Okay? So every time you ask that person and say, I'm running out of material to read, or I'm about to run out of material to read, the person will drive to the county library, which is a long trip. But that person will bring back up to 32 pages at a time. So that means, if you keep this up and you're reading in a particular order, and you don't skip the 32 pages that are already here, and you just keep reading sequentially, okay, you read 1 page after another, and so on and so forth, then you will be kept busy because the round trip to the county library is probably shorter than 32 minutes. Are we making any sense so far? But what if the way you read the document that is already brought back is, oh, by the way, I'm going to skip 31 pages after reading this page. Then the cache content, or the other 32 pages that the other person brought back, is useless. You will be waiting again. Okay? Are you guys relating what I just, the analogy to what we have here at, why we want to search linearly from 0 to and up? Yep, go ahead.
Well, if cache is so useful, why are we cleaning the browsers from cache?
That is a different type of cache. Okay, the browser's cache is using the same concept, except it is not related to the memory of your computer anymore. The browser's cache is basically stored mostly on a disk. Sometimes it may be preloaded a little bit, maybe in RAM. But the speed difference has to do with how long does it take to grab a page from a website as opposed to grabbing the same page from your hard drive. Your hard drive is still a whole lot faster than going out to the internet to grab a web page. So it's the same concept, except in the case of web caching, most of the time the browser does not do look-ahead caching. In other words, the browser would only cache whatever you have seen so far, but it won't go to all the links, potential links of a page, and pre-cache all those links as well. Okay? In the case of a processor, it does. In the case of a processor, if the processor says to the memory controller and say, I want that particular page, I want that particular location, the content of that location, depending on the access pattern, the memory controller can say, okay, I will give you not only the content of that location, I will also go ahead and grab the 16 locations, including that location. So it will grab a bunch of locations at the same time. Now you might say, but that can be wasteful because what if I don't need the other 15 locations after the location that you request? But the problem, the thing is, now that we have DDR2 and DDR3 memory, the cost of getting 15 additional memory locations is not really that much. Are you guys kind of seeing what I'm saying? Okay. So in other words, accessing and returning the content of one location and grabbing the content of the 16 locations, including the one that you want, the additional cost of getting 15 more pages or 15 more locations is not that much. And that has to do with DDR2 and DDR3, which stands for Double Data Rate version 2 and version 3, because they can be set up to access sequential locations very, very efficiently. Are we doing okay so far? Now, you can also remember, for some of you who configure your own computer, the memory is specified by DDR2/DDR3 depending on your motherboard, and it is also specified by a clock speed. Okay? The most common clock speed these days with DDR3 for a modern processor is 1.333 gigahertz, which basically translates to 1.333 billion memory cycles per second. But that's only if you do it in burst mode. Okay? That's only if you do it in burst mode. In other words, you access not just one location, but also the 15 locations after the location. If you access memory in that fashion, then it can transfer 1.333 billion times per second. If you access one location at a time, then the maximum bandwidth or the maximum transfer rate is much lower than 1.333 gigahertz. So what is that telling us? We want to read sequentially. That's basically what the bottom line is. You want your program to access data in a very sequential fashion. So this way, you read one location, it brings back the 32 locations, including the one that you want, and then you can keep processing. The processor can work with the cache for the most part until it runs out of the content that is already stored in the cache. Then it can go ahead and perform another burst read in another 32 locations. So that way you can keep your processor busy most of the time. If you access in a random fashion, like what we are doing here, then the look ahead is not going to help anymore, because you don't really care about the next 4 locations that you're bringing back, and as a result, that's all going to waste. Because the next time you have to read something, it is not something in the cache, and then you have to wait for the memory bus. You basically have to wait for someone to go to the county library to grab the next page and come back and process it. Are you guys doing okay with the analogy? And understand why we want to go in a linear way instead of a jumping around the code way, jumping around the array. Okay. Yep.
Is there any advantage to doing it in the random search way then? Like instead of having to look ahead of 6.
It is an obfuscation approach. Okay. If you want to hide how you access data in a certain way so that people who want to hack into your program cannot figure out the pattern, you might want to do something like that. So there are particular situations where you want your program to be less susceptible to hacking, and this way, people cannot use automated means to look through or to analyze your program, how it accesses data, and try to figure out a way to break into your program.
But then the end user who finally buys your product at the end would suffer from that part.
Yes, you will lose a lot of performance. Yep. It does not seem very important to us, when we're only concerned about software, but when you combine, how the hardware is going to perform this operation, you will realize that this is actually going to break what we call breaking the pipe, all the time. And as a result, all the cool, nice features of your processor will no longer be useful at all. Question? Okay. Any other questions? How many people are convinced that your memory, even with a 1.333 gigahertz memory, DDR3, your memory is still considerably slower than what your processor can process?
So if you're writing your algorithm in Ruby on Rails, does it really matter since it's so slow already?
I do not know. I don't know, how much of Ruby on Rails can be cached, because you're caching not only the data that you're processing, you're also caching the instructions that your processor needs to execute in order to run the program. So the limiting factor can be the instructions in the case of Ruby on Rails, because in order to interpret, it's an interpreted language. So in order to execute one single line of your program, it has to access a lot of instructions already. So that may be the bottom line. That may be the bottleneck already. But when you're talking about C and C++, which translate very nicely into assembly language and very tight loops too, this can become a major issue.
Yeah, I've heard that argument that with interpretive languages, but it doesn't matter because computers do it so fast. Get done.
Yep, I can believe that. I can certainly believe that. Many years ago, I had the opportunity to work on a project where the processor has a particular amount of cache, and it was crucial in that case that the software keeps everything in the cache, because if we lose that cache containment, then the program executed just slow enough that it was no longer acceptable. Any other questions? And by the way, how much processing power do we have with a modern day processor? Let's even just say let's just talk about a Intel Core i3 processor, which is the lowest line of the entire Core i lineup. It has 2 cores. Okay, so you will think, well, 2 cores is not really all that much processing power, is it? Okay, you have 2 cores, but the question is, how much processing resources do we have per core? Can it only perform one calculation at a time, or can it perform multiple calculations at the same time? One core has multiple what we call ALUs, arithmetic and logic units. In other words, a single core can already carry out multiple additions, subtractions, and comparisons all at the same time. Okay? And this whole thing, this entire thing, one single core with multiple ALUs, will run at the speed that it is rated at. These days, this can go from 2.4 gigahertz to 3.3 gigahertz, even without overclocking. So the question is, can you feed your processor quickly enough to utilize all the ALUs all the time and process the data all the time? And the answer is no. It is really hard to keep your processor occupied all the time. Okay? Because the memory bus is not only used to grab the data to process, grab the array element to compare to K, but it is also responsible to grab the instructions that will actually perform the comparison and whatnot. So most of the time, you are bound by how quickly you can talk to the memory, because remember, sometimes you have to store the result back into memory. So once again, it has to rely on the memory bus. Okay? And that's why, if you have a quad-core processor, but you don't have, fast RAM, it's not going to do you any good. Even if you have the top of the line, memory and a quad-core processor, you may not see any advantage over a dual-core processor unless you have the right type of programs. Like, if you have Ruby on Rails programs, it may not be very beneficial because you will still be limited by the memory bus. Okay? Are there any questions at this point about, why we need to look into the hardware implementation of caching and DDR2, even though we are talking about software in this case? No questions? Okay. Just a little bit of extra stuff, but I thought it is important to at least have you guys exposed to the interaction between, software and hardware, because something that seems just completely irrelevant from the software perspective actually has a lot of implications when it comes to the hardware operation of your computer. Okay, so now we are down to revision 3. So in revision 3, we can say, assume we search linearly from the beginning to the end. Okay. Now, once we have that assumption that we are searching linearly, and also from the beginning to the end, then we can actually